Chapter 9 is on nuclear chemistry. So half-life is the time it takes for half of the sample of your radioactive material to decay. It's symbolized by T1/2 for half-life. So for example, I have iodine 131 here. Its half-life is 8 days. So on the left-hand side of my chart is the grams of iodine 131. On the x-axis, I have the time in days. So my y-axis over on my left here, I'm starting with 20 grams of my sample. That's my original iodine 131. That's going to be decaying into another type of radioactive isotope or another type of element that might be stable. So when it decays, I start with 20 grams. When 8 days go by, I now have 10 grams. So one half-life, I have half the quantity I originally started with. Another 8 days go by and I go from 10 grams down to 5 grams. And I could just keep going. Another 8 days go by and I go from 5 to 2.5 grams, etc. Till eventually it's going to be gone. For strontium 90, this is a beta emitter. I want to know what my reaction product is going to be. What is it going to decay to? So again, beta emitter, we want to write down our symbol for that, 0, -1e. My new product, my mass number is going to always be the same, so it's 90. I have 38 plus 1 equals 39 to tell me the identity of my new element that strontium is decaying to is Y, which stands for yttrium. So basically the half-life of strontium is 28.1 years. So it takes 28.1 years for half of the material I start with to decay into yttrium 90. So down here I have, if I had 40 grams of strontium 90, after 28.1 years, I'd have half of 40 grams, I'd have 20 grams left. That means the other 20 grams was converted into yttrium. After another 28.1 years, I'd have half of my 20 grams and I'd have 10 grams left. So this chart shows us some half-lives of some various radioactive isotopes. For example, we looked at iodine 131. Its half-life was 8 days. And then we just looked at strontium 90, which had a half-life of 28.1 days. It's not listed here. But just to give you some ideas, they vary tremendously in time from one isotope to another. Look at uranium-238, 4.5 times 10 to the 9th years. That is billions of years long. Carbon, 5,730 years. Again, long half-lives. Iron-59, down we're talking about days. So it varies from one isotope to another, how long their half-life is. Your half-life for the specific element will always be given to you, and then you might need to do a calculation with that. Another way we can look at half-life is by the percent of sample we originally have and how much percent we have left. So in this example, we have the decay of Pu-239, which is plutonium. And if we look at the beginning here, we're saying we have 100% of our sample. So let's say maybe we had 20 grams. When one half-life went by, we'd have half that amount, so we'd have 10 grams. Or we can just look at percent. So if I start with 100%, in one half-life, I have 50% of what I originally started with. So for plutonium, it has a long half-life, 24,110 years. So in 24,110 years, I have 50% of the original amount of plutonium I started with, no matter what the quantity is, it's just 50%. After another 24,110, I'm now at 48,220 years. I have half of 50, which is going to give me 25. So I have 25% of the original material left. And as you can see, you can keep going with your half-lives. So in this example, we go to 96,440 years. We have 6.25% of the original sample of plutonium-239 left. In this half-life example, we have 10 milligrams of iodine 131. Its half-life is 8 days. This iodine 131 is given to our patient. We might want to be checking to see if their thyroid is working properly. We want to know how much is left in our patient, in their body, after 32 days. So we can go ahead and calculate this out. we know we have 10 milligrams is the amount of iodine-131 they were given. In 8 days, that's the half-life, we're going to have half that quantity. So 10 milligrams, we're now going to have 5 milligrams. Another 8 days goes by, we have half of 5, so we have 2.50 milligrams. Another 8 days go by, we have half of that, so we have 1.25 milligrams. And then another 8 days go by and we have half of that, 0.625 milligrams. So if we count up all these days, we have 8 plus 8 plus 8 plus 8, or 8 times 4, which gives me 32 days. So the quantity I have left after 32 days is 0.625 milligrams. And then that's how much I'd have left in my body after approximately a month. In this half-life example, you are given 350 grams of barium-122, which has a half-life of 2 minutes. You want to know how much barium-122 will you have after 10 minutes go by. So again, we're going to start with our 350 grams of barium-122. And after 2 minutes, we're going to have half that quantity. So that's just 350 divided by 2 is 175 grams. Another 2 minutes go by. We divide our number in half, 175 divided by 2, and we get 87.5 grams. Another 2 minutes go by. 87.5 divided by 2 gives me 43.75. Another 2 minutes, so far we've gone 8 minutes. We have half of that number is 21.875 grams. We're going to have to curve down here. Another 2 minutes go by. Because we've done 8, we need one last one to get 10 minutes. Half of 21.875, we get 10.938 grams. And we originally started with 350.0, which is 4 sig figs. So our final answer should also have 4 sig figs. So let's reduce 10.398 to 10.94 grams of barium-122. So again, we can add up. We have 2 plus 2 plus 2 plus 2 plus 2 gives me 10 minutes when I add all my 2 minutes together. So carbon-14 dating is used to determine the age of archaeological objects. And this is used based on the half-life of carbon-14, which is 5,730 years. The idea of how this works is carbon-14 is a radioactive isotope of carbon. And the carbon-14 will react with oxygen in the air and form CO2, which is radioactive. And plants need carbon dioxide, because remember, the plants breathe in our CO2 when we exhale, and then they create oxygen for us. So the plants, we can actually measure the amount of carbon dioxide of a plant, or radioactive carbon in a plant, based on the amount of carbon dioxide they've brought into their system, and compare an item that's old compared to new. So for example, if I had a tree today, I can measure the amount of radioactivity in my tree that's due to the carbon in the tree. And then if I had something made from a tree, let's say maybe a mummy's coffin made of wood, okay, I could measure the radioactivity from both of these and I could compare, because once the tree dies, it's not going to be absorbing any more CO2, so the amount of carbon radioactivity is going to change. It's going to be decaying, and we can determine the half-lives to determine how much has actually decayed. So again, we can measure radioactivity of something new, like our tree, and then measure the radioactivity of the wood in something that's been, dead for thousands of years to give us an approximate age of how old that mummy coffin might be. Or you could also think of maybe cotton is a living plant, and mummies were wrapped in cotton wraps. We could also date how old was the actual mummy that might be, inside of here. Okay, so in this example, using carbon-14 dating. We're actually using fresh charcoal, which fresh charcoal is made of pure carbon. And you could measure a piece of fresh carbon in our charcoal today, and it gives off 13.70 disintegrations per minute per gram of carbon. So this is just a unit to measure radiation. Don't worry too much about the units here, but it's just saying for every gram of carbon, if I had an instrument, I would measure this many disintegrations. And then we went to this cave painting, which this is a famous cave painting in France. We could take a piece of charcoal. Okay, they use this charcoal to draw this cave painting. We could take a little piece of that charcoal here and measure the amount of radioactivity coming off of that actual sample here. And when we measured that, we found off it gave 1.71 disintegrations per minute, which makes sense because the older it is, there's going to be less carbon present because it's been decaying into something else. So we can figure out how old this cave painting is by using our half-life method. So instead of saying a quantity like how many grams, we can just say we're starting with disintegrations of today of 13.70 disintegrations per minute per gram. The half-life of carbon is 5,730 years. So after 5,730 years, the amount of carbon is going to be half the quantity, so the disintegrations is going to be half the amount. So half of 13.7 gives us 6.85. Another 5,730 years go by, and the amount of disintegrations per minute is now 3.42. Another 5,730 years go by, the amount of disintegrations is 1.71 grams disintegrations per gram of carbon. So now we can figure out how old our cave painting is that contains the charcoal in it, the carbon, because we have the quantity we're looking for. So this was 3 half-lives that went by, so we could add up 5,730 plus 5,730 plus 5,730, or just multiply by 3. And the age of our cave painting is 17,190 years old. Now, half-life is an approximate method, plus or minus a few hundred years, I would say at least. But it does give us an idea that we can determine how old these archaeological objects are by using carbon-14 dating. This slide shows us our average exposure to radiation is about 359 millirems per year. The millirems is actually another type of unit that we can express radiation. Like in the previous example, we have disintegrations. There's numbers of different types of units, so you don't have to worry too much about being familiar with the units. But this is just showing us per year. You don't have to remember this number. What I want you to get from this chart here is we're looking at naturally occurring radiation sources and artificial radiation sources. So under naturally occurring, we have cosmic, we have terrestrial radiation, which is going to be, again, your geology of the area that you are living in. You know, if your building's made of concrete. You have radiation inside your body, in your bones. You have radium-226 and potassium-40. But if you look at these levels, they're pretty small compared to the largest source of naturally occurring radiation is radon. And again, that's that radioactive isotope that's a gas at room temperature, and it's found in the air. So that's something that we're breathing in. So we have about 294 millirems coming from naturally occurring sources versus artificial, whether we're looking at x-rays, nuclear medicine. Again, this is going to vary from each person to each person. Consumer products like makeup, there's certain cosmetics that have radioactive isotopes in them. Nuclear power plants, notice the quantity here is very small because again, our nuclear power plant has those concrete containment walls around it to protect us from the radiation inside. So the amount here is about 65 millirem per year for artificial radiation compared to naturally occurring, which is 294. So average is about 359 millirems per year. So what I want you to take away from this chart is if you're exposed to more radiation from naturally occurring sources versus artificial, and obviously naturally occurring is much higher than our artificial radiation. And again, this is on average. So as I said, there are a lot of naturally occurring sources of radiation. Food is one of them. So question here is, which food is the most radioactive, if you had to guess? So we have Brazil nuts is the highest amount of radiation that's known out there. Other sources, we've got lima beans, bananas. Again, bananas contain potassium in here. So potassium has a radioactive isotope. That's why our banana is glowing down here. But I don't want you to think I shouldn't eat bananas or Brazil nuts or lima beans. Those are all things that are good for you. It's just showing, again, there's very, very small levels of radioactive isotopes in here. We have listed down here, we have radium and potassium, both of them listed, that are inside these foods. But not enough to make it worth not eating. The health effects are obviously much better. Other foods that contain radioactive isotopes, we have carrots, potatoes, French fries, because French fries are made from our potato here. These also have radioactive isotopes in them. But again, the only one I would say probably don't eat for other reasons is your French fries, but definitely please keep eating carrots, potatoes, Brazil nuts, and all those other things. There's just naturally occurring sources of radiation, very low levels that you don't need to worry about it. In this slide, we'll be looking at the radiation effects of various doses on your health. And previously we said what you're exposed to on average from natural and artificially made sources of radiation was about 359 millirems, and that was per year. So I want to go ahead and put your average exposure instead of using millirems into rems, because the numbers we have on this page here are all in rems. So again, remember, a milli means 1/1000th. Okay, so a millirem is 1/1000th of a rem. So if we divide by 1,000, we get 0.359 rem per year is on average what we're exposed to. So if somebody had cancer and they were going in for treatment, they may be exposed to about 100 rem. So I wanted to do sort of a comparison here. And this is, in a one-time shot versus we're exposed to 0.35 rem per year versus 100 rem per, dosage. So that high quantity is what you're using to treat cancer. That's going to cause radiation sickness. When people are losing their hair and they're feeling nauseous from undergoing cancer treatment, radiation treatment. So these numbers I do want you to know. So 100 rem causes radiation sickness. If you were exposed to 400 rem, this is again on average, 50% of our population would die in 1 month from a one-time exposure to that. If you're exposed to 600 rem, everyone will die. Okay, that is lethal for everyone at that high of a dosage. So know these different numbers, 100, 400, and 600, and what the effects are to that kind of quantity. Nuclear fusion is when two nuclei combine to produce a nucleus of a heavier mass. And if you think about the word fuse, fuse means to combine. So if we have two things to come together, they can fuse together or combine to make one thing. And that's basically what's happening with nuclear fusion. So these type of reactions can only occur when you have very high temperatures. For example, in the sun, where the temperature is above 440 million degrees Celsius. So here's an example of a fusion reaction that occurs in the sun. We have H2 and H3, these different isotopes of hydrogen. And we're showing it pictorial over here on the right. So H2 is deuterium and H3 is tritium. So again, in H2 we have 1 proton to 1 neutron. In tritium or H3 we have 1 proton, because again hydrogen always has 1 proton, and we have 2 neutrons. So these two different atoms of hydrogen come together, they combine, they create here, they're combining, the two are combining together, all of their protons and neutrons are here in this, and when we have 2 protons, we create helium, and this is not stable here. So what happens is this kind of breaks apart, gives off energy. We have our helium left behind, and then we're releasing one of the neutrons. So this is giving us the energy that's being produced in this reaction, and we're producing, again, a helium and a neutron here. So the main thing to get from fusion is fusion reactions are we're going to be combining two things together. We're going to create something that is larger. So if we look at our mass numbers, we have a mass number of 2 and 3, and then we're combining to create something larger. It's got a mass number of 4. So I'm not going to expect you to remember, any exact reactions, but be able to identify if it's going to be fusion versus fission. Fusion, again, is combining. We're creating something with a larger mass number, and fission we'll talk about next. Nuclear fission is the opposite of fusion in the sense that we have large nuclei that are breaking apart into smaller nuclei instead of combining and creating something greater. So we go from a larger nuclei into a smaller nuclei. Nuclear fission is what's used in nuclear power plants, and that's where we get our atomic energy. The same exact process is in a nuclear bomb or an atomic bomb. It's the same idea with both of these, and we'll look at what the difference between a nuclear power plant is and a nuclear bomb. So here we have in our example. The other thing that happens is here I have my original nuclei. I have uranium-235. I'm going to be bombarding it with neutrons, and then I'll be producing energy in this reaction. So here's my neutron. My N stands for neutron. So I use my neutron, I hit the uranium-235, and initially it combines and we get 236. Okay, but this is not stable. That's what these brackets here mean. This is not stable. This is what's going to break. Okay, so it breaks here. This is what I would call is an intermediate. It doesn't last. It immediately breaks apart once it's formed. And in the breaking process, we're creating elements here that have smaller mass numbers than what we started with. So we had 235, and now we have a mass number of 141 for barium and 92 for krypton. So they have smaller mass numbers. We're also producing more neutrons. We started with 1 neutron, and now we have 3. So this is kind of showing us down here using this picture view. Here's my atom of uranium-235 that I started with. I'm hitting it, bombarding it with this one little neutron. I'm producing krypton, barium, and then I produce 3 more neutrons. These 3 neutrons are going to go react with 3 more atoms of uranium, because remember, we don't have just one atom of uranium. We've got a certain quantity of it, so there's a whole bunch of atoms. They're going to go on and keep reacting, creating more neutrons. So we get this chain reaction that occurs. So we call this a self-propagating chain reaction because we're producing more neutrons. Those neutrons produced will react with other uranium-235, increasing the rate of the reaction. And what happens in a nuclear bomb or an atomic bomb is it keeps going and going until it actually explodes. So this is this self-propagating reaction. It keeps going, keeps going. Eventually it can't handle anymore, and there's so much energy created, the whole thing just explodes. Nuclear power plant is a little bit different. It's actually controlled, where you're going to be removing neutrons from the reaction. So I'll show you a picture of how you can remove the neutrons. So nuclear power plants use nuclear fission to create energy, essentially. So what we have here is on the outside, we have our containment structure. So this would be our concrete wall, which would look like your domes if you were to drive by from the outside. That's to contain any of the radiation inside our reactor. So this is the reactor vessel. It has what we call here fuel rods. The fuel rods contain the uranium in there, and that's our radioactive isotope. So that's going on in here. They're going to be adding neutrons to it, and the neutrons and the uranium react. We get this chain reaction going on. Now at the top we have what are called here control rods. The control rods actually absorb the neutrons. Okay, so the control rods, you can move those in and out of the reaction. So when you want the reaction to go, you pull your control rods upward so they're out of the reaction. You're creating energy that can be converted into steam. Using your generator, you can create electricity to power your city. When you want the reaction to stop, so before it's going to actually explode, you put those control rods back in. Those control rods then are made of material that can absorb the neutrons, and that will stop the reaction. So that's how you can control your nuclear fission process, is with these control rods. So nuclear power plants, are a good source of energy. The concern would be if for some reason the reaction got out of control, you could potentially explode just like a nuclear bomb. This slide is in here to show you what a nuclear explosion would look like. Again, a nuclear explosion is a nuclear fission reaction process where you have radioactive isotopes that are being broken into smaller atoms than what you started with and giving off energy, obviously, as you can see in this picture. So this is a nuclear test called Priscilla that was exploded in a dry lake bed northwest of Las Vegas, Nevada in 1957. Again, just to show you a photo of what a nuclear bomb would look like.